In the first video, Work, Energy and Power Part 1, we have studied the definition of the term work as used in physics and also the work done by a constant force. Continuing the same unit, in this present video, Work, Energy and Power Part 2, will be calculating the work done by a variable force. In fact, the forces in nature are very rarely constant. In general, the forces applied continue to change. The work done by such a force can be calculated by two methods. The first one is the graphical method. Let us suppose we have a variable force represented by this graph DC as the body is displaced from point A to point B. The work can be calculated by graphical method. For the purpose, what we do is we divide this distance AB into a very large number of small parts. One such part is shown by P1, P2. Similarly, we divide the entire region AB into extremely small strips. If we consider one strip P1, P2, one such very small strip P1, P2, and the force here, as you can see, the force for displacement from P1 to P2 shows a very small variation. The force at P1 is P1 Q1 and force at P2 is P2 Q2. The variation in the force, as you can see from the diagram, is very small. If P2 approaches P1, the force may be considered as constant, that is equal to P1 Q1. So here for this infinitesimal small distance P1 P2, the work done dW, a very small amount of work done dW, can be calculated as the force P1 Q1 assumed constant under the condition P2 approaching P1 as product of force P1 Q1 and the distance P1 P2, which is also equal to area P1 P2 Q2 Q1, that is area of this strip. This is the work done for a small displacement from P1 to P2. So if you want the total work done as the force is displaced from A to B, we can do it by dividing this region into a large number of strips and adding areas of the strips. So total work will be sum of areas of infinite strips equal to sigma f dx, or given by area under F versus X, that is force versus displacement graph. Therefore total work is limiting value of this sum f dx subject to the condition that dx or P1 P2 approaches 0, equal to total area under the graph from A to B, or area A, B, C, D, A. This area under the graph gives the work done. There is one thing which needs special mention here. When you calculate work done by area under F versus S graph, the area above the axis is to be taken as positive because this represents positive work, and the area below the graph is to be taken as negative because this signifies negative work, and the total work will be algebraic sum of the areas above the graph and below the graph. Now moving on to the second method, that is mathematical method of calculating the work done by a variable force. Suppose we have an object A, object at point A. subjected to a variable force F, which may change in magnitude, which may change in direction, and it is moved from A to B, with AB representing the total displacement. Here again, in order to calculate the work, we need to divide this total displacement AB into a large number of small parts between A and B. PQ represents one such small part. Take PQ as ds, a very small displacement from P to Q. As ds approaches 0, the force may be taken as constant, because very small displacement means very small variation in the force. Therefore, force can be assumed to be constant. We calculate a very small amount of work done for this infinitesimal displacement ds as dw is equal to f dot ds, f vector dot ds vector, which will mean f ds cos theta, theta being angle between the force vector and the displacement vector. So we'll have to calculate work over all such elements. PQ can be here, next part, and so on. So total work for the displacement from A to B will be sum of these small amounts of work done over extremely small displacements ds. So work will be sigma f dot ds over the entire displacement A to B, which by definition mathematically is integral of f dot ds as the body moves from A to B with displacement from A to B. The work done may be positive or negative. When you calculate this integral, the sign will automatically appear. Let's take an example of variable force. You can see here we have a spring attached here, fixed with one end fixed here. For an elastic spring, the force is proportional to the extension. The larger the extension of the spring or the compression of the spring, the force will proportionately or linearly increase for an elastic spring. So here, as you move this free end of the spring towards right, the force keeps on increasing, which indicates that the force is a variable force. Now in the next part of this video, we take up some illustrative examples for calculating the work done by constant force and work done by variable force. To clearly understand the definition of work which we have studied, let's now take some illustrative examples. Example 1. A 50 kg wheat bag is to be delivered in a flat at a height of 10 meter from the ground level. Calculate the work done by the delivery boy and by the force of gravity. The situation is shown in figure 1 and figure 2. Here in figure 1, in order to carry the bag, the delivery boy has to exert a force upwards, and the displacement is also upwards. So the force and the displacement are in same direction. Therefore, angle theta between the force and the displacement vector will be 0. So we have F applied equal to mg because the force of gravity is to be overcome, which is equal to 500 Newton, taking g to be 10 meter per second square for simplicity. And the displacement is 10 meter, and the work done will be F into SF dot S equal to Fs cos 0 equal to 5000 Newton. For the force of gravity, the situation is shown here. The force of gravity, that is mg, acts downwards, vertically down, and the displacement is upwards because the bag is being carried upwards. The angle between the force and the displacement in this case, as also shown in this diagram, and the downward S upward is 180 degree. Therefore, work done will be Fs cos 180 equal to minus 5000 joule. Now, you can apply this solution to 1 in a similar manner to this problem. We have a block being moved from X to Y by a 50 Newton force applied by an agent and opposed by B as shown. B may be another agent or may be the force of friction. You have to calculate the work done by A on the block, by B on the block, and verify that the total work done is equal to the work done by the resultant force. Let's take another example. A force F Newton acting on a particle varies with position x as F equal to 2x plus 5 I cap. Calculate the work done for a displacement from x equal to 2 meter to x equal to 5 meter. Here we are given F equal to 2x plus 5. Therefore, as position changes, the force value of force changes. If you take a very small displacement dx, the work done for the small displacement will be given by F dx, which means 2x plus 5 dx. The work W for a displacement x equal to 2 meter to x equal to 5 meter can be obtained by integration. If you integrate this 2x plus 5 function, you get x square plus 5x by usual integration formula, and substituting the limits, upper limit minus the lower limit, the work comes out to be 36 joule. The same problem can also be solved by means of this graph. The force versus x graph, since it's a linear equation, F equal to 2x plus 5, the graph is a straight line as shown. So here you can get the work done by taking area under this graph. Okay. For x equal to 2, you can calculate F from the graph, which will come out to be 9, and for x equal to 5 meter, again you can get the value of the force from the graph. By finding out area of this trapezium, you can get the work and verify that you get the same result as you get by integration method. Example 3. For an elastic spring, the restoring force is given by F is equal to Kx. The restoring force is the force which is set up in the spring when we pull the spring or compress the spring. This is a force which opposes the extension or compression in the spring. The spring is elastic if F is of the form F equal to Kx. K is called spring constant and depends on nature of the spring, and X is the extension or compression produced in the spring. Calculate the work done to produce an extension A in the spring. For an unextended spring shown in this figure, first figure, there is no change in length and has no restoring force. If you produce an extension X, the force required to pull the spring will be Kx as given by this formula. So for an extension X in the spring, we have F is equal to Kx. If the spring is further stretched through an infinitesimally small displacement dx, then the work done will be given by F dx or Kx dx. Clearly it's a variable force. So the total work done for an extension from 0 to A has to be calculated either graphically or by integration. Using integration method here, we will get the total work W as integral dW or integral kx dx, the limits 0 to A. This is for unextended spring, x equal to 0 to a maximum extension A. The integration leads you to this result, kx square by 2 limits 0 to A, or substituting the limits, the total work comes out to be half ka square. Here are a few problems for practice which will help you reinforce what you have learned in Work, Energy and Power 2 videos, parts 1 and part 2.